A very useful and common way to display how the concentrations of reactants change over time, and therefore how we can study kinetics, is by just plotting the concentrations over time, as of course you may have guessed already. The idea is as you will see, the slope of this curve tells you how fast reactants disappear and products appear. So in general, these curves represent, you will see two types of curves, some curves going down and some others going up. The ones that go down are the ones that with time the concentration disappears. We typically call this reactant, and the concentration that appears with time we call this product. Okay? There will be some cases in which, like in this case, you have two types of reactants and you have two different coefficients. Now, which one is which? What you see in this plot is that you have the red curve and the green curve. The red curve has a much larger slope, if you will, so it changes more with time. And notice that the way we read the stoichiometry in this reaction is that for each mole of fluorine that becomes products, there is 2 moles of nitrogen dioxide that become products. Therefore, B will be nitrogen dioxide and C will be fluorine. Again, because just by looking at the slope, not necessarily the concentrations, we could have started the concentrations at the same point, so let me just do that, what it would look like. If we had started with equal amounts of concentrations of NO2, so NO2 would have disappeared faster than F2, okay? This being F2, this being NO2. And what it's clear that if there is a 2 in reactants and a 2 in products, the NO2F will have to be, it's the only product in this case, but it'll have to appear at the same rate at which the reactants disappear. Okay? Some critical thinking questions. Do reactions ever stop? Well, from the macroscopic point of view, yes, there will be a point at which the concentrations at this time, the concentrations are constant. So you could say when the concentrations are constant, you have reached the equilibrium. However, it's a dynamic equilibrium. This means that reactions actually never stop. There's always some moles of reactants becoming products and some moles of products becoming reactants. Actually, equilibrium is reached when the rate of moving forward is equal to the rate for the reaction moving backward. So reactions at the microscopic level or the atomic level, they do never stop, but the concentrations remain constant at some point because you have reached the equilibrium. So the same number of moles become products, then the same number of moles becoming reactants. All reactions are work in both ways, so all reactions are both directional, bidirectional, we could say. So let's practice a little bit. In this case, we're being offered one reaction in here, and we are being asked again what curves represent what component. The first step is, well, if the reactants will be disappearing with time, therefore nitrogen dioxide will be disappearing with time. And notice that for each mole of nitrogen dioxide there will be 2 moles of nitrogen monoxide and 1 mole of oxygen. So oxygen will appear not as fast as the reactants disappear. So this will be oxygen because it does not appear as fast. For each 2 moles, only 1 mole, so half of those moles, will appear as oxygen. Therefore, this will be nitrogen monoxide. So which molecule appears faster? The change of concentration with time will be for nitrogen monoxide. It changes faster. So if you can think of just of the slope, and that's how we will define rate in our next video, the rate of appearance of nitrogen monoxide is higher than the rate of appearance of oxygen. Now, could this reaction be for the decomposition of ammonia? Well, there has to be that the rate of disappearance of products has to have a curve for the same appearance disappearance of one of the reactants has to be equivalent to the rate of appearance of some products. So if this were my ammonia, it would disappear and it would have to create nitrogen. Oops. Nitrogen. But you have a 3 here, so it means that there should be therefore a hydrogen that is being created at 150%, well in this case 50% more, right? So three halves of the rate of nitrogen. So this graph cannot represent this reaction because A is the product that appears faster. It only appears as fast as reactants disappear. So no, this is not the case for this reaction. A question that may help you connect with the equilibrium concept: does this reaction have an equilibrium constant larger or smaller than 1? Notice that in equilibrium, that is when at this point when concentrations remain constant, there is in equilibrium more products. The concentration of products in equilibrium is higher than the concentration of reactants in equilibrium. This means your equilibrium constant is larger than 1. You have a product bound reaction. Okay, if the curves of products were always below the curve of reactants, we would be in the case of a reaction with an equilibrium constant smaller than 1.